Welcome, everyone. Today, we're going to explore the fascinating world of transmission line design. The slide here is titled, Transmission Line Design Overview. We'll look at how electrical loads are calculated, with an example showing that for 230 kV and 400 A, the load is approximately 159 MVA. We'll also discuss how transmission line design ensures efficient power transfer while adhering to mechanical, electrical, and environmental limits set by SEC TES, TMSS, and TCS standards. Throughout the presentation, we'll cover key stages like design, calculation, installation, testing, and handover. So let's get started and delve into this essential aspect of power systems. Let's dive into the concept of environmental zones and design temperature. On this slide, we see the formula for calculating the sag of a structure, which is given by W times L2 divided by 8 times T. Here, W represents the load per meter, L is the span length, and T is the tension or strength parameter. For example, if we have a 300-meter span with a load of 1.1 kilograms per meter, and a tension value of 1,600 kilograms, the sag calculates to approximately 6.9 meters. It's important to understand that the design parameters will vary depending on the environmental zone. Coastal areas typically require anti-corrosion measures due to salt exposure, while inland zones might need higher mechanical tension to handle different stresses. Additionally, the maximum temperature we consider for these structures is around 55 degrees Celsius. These environmental considerations are essential because they directly influence the design choices we make to ensure safety, durability, and optimal performance in different settings. So, understanding how these factors interact helps us tailor our approach to each specific zone. Let's talk about the structural design and galvanization process. One key aspect here is the coating mass, which we measure in grams per square meter. To calculate it, we multiply the density by the thickness and then by 100. For example, if we take a density of 7.1, a thickness of 0.013, and multiply by 100, we get a coating mass of 923 grams per square meter. This coating mass is crucial because it determines how well the material will resist corrosion over time. According to the SEC TMSS standards, zinc coating levels vary depending on the environment. For coastal areas, the zinc coating is about 915 grams per square meter, whereas inland areas typically see around 610 grams per square meter. And interestingly, near shorelines, a duplex coating system is often used, which combines galvanization with additional protective layers for enhanced durability. So, understanding these coating specifications helps us design structures that are not only strong, but also resistant to the harsh environmental conditions they face. Let's talk about conductor configuration and transposition. First, the inductive reactance, which we denote as XL, is calculated using the formula 2 pi times the frequency times the inductance. For example, if we have an inductance of 1.5 millihenries per kilometer and a frequency of 50 Hz, the reactance comes out to approximately 0.47 ohms per kilometer. Now, to improve the transmission, transposing the conductors every 90 to 270 kilometers helps balance the phase reactance. This process minimizes interference between the phases, which is crucial for maintaining power quality and system stability. So, overall, proper conductor configuration and strategic transposition are key to optimizing the performance of the transmission line and ensuring reliable power delivery. Now, let's look at the ground wire and OPGW protection. The fault current, which is the current that flows during a fault, can be calculated using the formula V divided by the sum of ZL and ZG. Here, ZL represents the line impedance, and ZG is the ground impedance. For example, in a 230 kV system with a line impedance of 3 ohms and a ground impedance of 2 ohms, the fault current would be approximately 46 kiloamps. This value is well within the typical limit of 63 kiloamps for such systems. When it comes to OPGW, or optical ground wire, standards like IEC 61394 are followed. It's important to note that in certain zones, such as the Red Sea regions, conductors need to be greased to ensure proper protection and performance. The fault limit for these systems is set at 63 kA for voltages ranging from 230 to 380 kilovolts. Understanding these parameters helps us design and maintain reliable grounding and protection systems, which are crucial for safety and system stability. Let's talk about insulator strings and hardware assembly. The number of discs you need is calculated based on the voltage level, specifically V divided by 15 kV, for example. For a 230 kV line, you typically use around 16 discs, and for a 380 kV line, about 25 discs. This helps ensure proper insulation and safety. According to TES P122-4R03, there's a distinction between suspension insulators for straight sections and tension insulators for angles. The creepage distance, which is the path along the surface of the insulator, should be at least 31 millimeters per kilovolt to prevent tracking and flashovers. The key here is understanding how these components work together to maintain reliable and safe power transmission. The assembly and correct selection of insulator strings are critical for overall system performance and safety. Now, let's move on to the installation and field testing phase. One of the key concepts here is calculating the tension in the cable, which is crucial for ensuring structural integrity. The formula we use is tension equals the weight per unit length times the length squared, divided by 8 times the sag. For example, if the weight per meter is 1.1 kilograms, the span length is 300 meters, and the sag is 6.9 meters, then the tension comes out to around 1,435 kilograms. It's important to perform thorough testing after installation. This includes waiting for the foundation to cure, which typically takes about 28 days. We also need to verify that the earth resistance is less than 10 ohms to ensure proper grounding. The insulation resistance should be greater than 1,000 megohms to guarantee electrical safety. Lastly, we aim to keep the sag within a plus or minus 3% tolerance to maintain optimal tension and system performance. These steps are vital to ensure the durability and safety of the installation, aligning with our overall goal of reliable, efficient power transmission. Now let's talk about the final stage of the commissioning process: documentation, inspection, and handover. The total commissioning time is actually the sum of 3 key phases: T1, T2, and T3. For example, it might take 10 days for documentation, 5 days for inspection, and 3 days for the handover, adding up to 18 days in total. During the final handover, we include all essential documents such as as-builts, inspection reports, approvals, and the energization certificate. These records are crucial because they ensure everything is properly documented and ready for operation. You'll notice the icons here: Docs, QC, Records, Energize, and Handover, each representing a vital step in this process. Proper documentation and thorough inspections are what guarantee a smooth transition from project completion to operational use. This phase really ties together all the work we've done and makes sure everything is in order for the client or end user.